A heat engine is a useful device. As you can see, we have a schematic of the thermodynamic process here. It's connected to a hot reservoir. Hot reservoir is an energy reservoir at a high temperature, TH, and it absorbs heat from this hot reservoir and operates in a cyclic process so that the initial state and final state are the same, and provides a work that this is the work done by the engine, W engine, and expels part of that energy to a cold reservoir as QC, heat released to a cold reservoir. So we can summarize this as we have an input energy QH. This is the energy absorbed from the hot reservoir. We have a useful output. This is work done by the engine, W engine. And then we have wasted energy, QC. So I'm looking at this device from an engineer point of view. We are inputting some energy into the system, and the system produces a useful output work, but part of that energy is lost to a cold reservoir by means of heat. So because it's a cyclic process, you can see here there is a reason why we have this circle here, because it's a cyclic process. And what do we know about cyclic processes? The initial and final states are the same, so the internal energy of the engine does not change. So you have the total heat added to the system plus the work done on the engine must be equal to 0. So here I have to clarify that in this diagram I have W engine is the work done by the engine. So if you look at this equation, first law of thermodynamics, it's the heat added to the system plus the work done on the system. So what is the total heat added to the system? Q here is equal to QH, and there is part that is lost to the cold reservoir minus QC, and the work done on the engine is minus W engine. So this equation is basically telling me QH minus QC minus W engine is equal to 0, or W engine is equal to QH minus QC. This is basically conservation of energy in the system. And we can define the efficiency of this engine, the thermal efficiency. Basically it's a engineering parameter. So the thermal efficiency, I'm going to call it E. It's defined as the useful output divided by input. So in this case, this is going to be the work done by the engine is the useful output, and the energy that we're inputting into the system is QH. So if you calculate this efficiency, because W engine is QH minus QC from the first law of thermodynamics, divided by QH, This tells me that the efficiency of this engine is 1 minus QC over QH. Alright, so it's quite clear that if we are going to engineer such a device, a heat engine, we would like to have QC is equal to 0. So efficiency equals to 1 would imply QC is 0. Alright, so here is the point where we have trouble, because there is the second law of thermodynamics, Kelvin-Planck form. So what does this say? Basically, the second law of thermodynamics states it is impossible to construct a heat engine that operating in a cycle produces no effect other than the input of energy from a reservoir and the performance of equal amount of work. So that's the statement, Kelvin-Planck statement. Basically, it's saying QH is equal to W engine, or QC is equal to 0. This is not possible. In other words, in our diagram here, you can see we have a cyclical machine that absorbs heat from a hot reservoir and provides an equal amount of work with nothing expelled to the cold reservoir. This is not allowed by the second law of thermodynamics. In other words, the thermal efficiency of a heat engine cannot be equal to 1. So we cannot have a 100% efficiency heat engine. Now we have a similar device. It's called a heat pump or refrigerator. It's basically the reverse of the heat engine. You can see that we are doing work on the engine, on the pump. It extracts heat from a cold reservoir and provides heat to a hot reservoir. So that's almost the reverse of the heat engine. Okay, so if we want to summarize what's going on here, we have input energy is W. We have useful output this can be QH, useful output QH, or it can be a useful input QC. It depends on how we look at the operation of this machine, so we can define what is useful for us. So what do I mean by this? If you think about your air conditioners that have an inverter, so in hot summer days you use your air conditioner to cool your room, in cold winter days, you can use your air conditioner with the inverter to warm up the air inside the room. So we can use it in both ways. In the hot summer days, what we are doing is basically providing heat to the to outside. So that's QH that we're providing, and we're extracting heat from the cold reservoir, which is your room. And what is useful for us is the energy that we're extracting from the room, QC. On the other hand, if you have a cold winter day, then we want to have a lot of heat provided to a hot reservoir by our inverter air conditioner. It's going to extract heat from the cold reservoir that's outside and provide heat to the hot reservoir that is your room in order to warm it up further. Okay, and now we can provide, for example, an example for this. If you look at your refrigerator, it has two sets of coils, and so this heat pump has a circulating fluid that passes through these two sets of coils, and it's in this cycle it goes through a low pressure part where the fluid is cold, where it absorbs heat, and then the warm fluid is compressed and enters the hot coils, the high pressure fluid, where it releases heat to warm the surroundings. So your refrigerator actually can be used to warm up your room as well, because it provides some of the heat to the surroundings. Okay, now if you want to talk about the first law of thermodynamics for this heat pump, basically you will say that again this is a cyclic process. So I'm going to have no change in the internal energy, and then I ask myself, what is the heat added to the system? The heat added to the system is QC minus QH, and what is the work done on the system? W. So this is equal to 0. So I have W is equal to QH minus QC again for this cyclic process. And now we can talk about the efficiency of this in two different ways, as I said, whether we are using it as a heater or a cooler. So in order to distinguish these two, we define the coefficient of performance instead of thermal efficiency. Coefficient of performance, COP. So this is going to be what you gain divided by your input. So coefficient of performance, if we are using this device in the cooling mode, then this is going to be equal to the energy that we're extracting from the cold reservoir divided by the work done by the on the engine. If you're using this in the heating mode, then it's going to be QH, the energy that we're providing to the hot reservoir to warm it up further, divided by W. So we have two definitions of efficiency for the heat pump, depending on whether we're using it as a heater or a cooler. Now, if I look at these coefficients of performance, for this one, let me see what happens. Coefficient of performance in the cooling mode is QC divided by W, and I would like to have QC, which is QH minus W from my first law of thermodynamics, divided by W. So this will be equal to QH divided by W minus 1. And for coefficient of performance heating mode, I would like to have QH divided by W, and this is going to be equal to W plus QC divided by W, and this will be equal to 1 plus QC over W. Now, in order to have a very good coefficient of performance here, what we would like to have is W to be 0. You can see if W goes to 0, the coefficient of performance would go to infinity, right? So you would have infinitely efficient device. So we would like to have this device basically that extracts heat from a cold reservoir, provides heat to a hot reservoir without any input of work. So this is now the Clausius statement: such a device cannot be built. Okay, so let's see what the statement says. It is impossible to construct a cyclical machine whose sole effect is to transfer energy continuously by heat from a cold to a hot reservoir without the input of energy by work. So this is impossible. So it's again the second law of thermodynamics, the Clausius statement. Okay, so let's take a look at an example. A certain refrigerator has a coefficient of performance of 5. So first of all, I have to be careful with what this device is used as. It's used as a refrigerator. So in the refrigerator, I have a cooling mode. Cooling mode. All right. So what is the coefficient of performance in the cooling mode? I should have the energy that I'm extracting from the cold reservoir divided by the work that I'm inputting into the heat pump. This is equal to 5. When the refrigerator is running, its power input is 500 watts. So we're inputting electrical power, 500 watts. This is the work done on the pump per unit time, delta T. So the work done on the pump is going to be equal to 500 times delta T. A sample of water of mass 500 grams and temperature 20 degrees Celsius. So I have water 0.5 kilograms, initial temperature 20 degrees Celsius, It's placed in the freezer compartment. How long does it take to freeze the water to ice? Finally, I have 0 degrees Celsius ice. Assume all other parts of the refrigerator stay at the same temperature. There is no leakage of energy from the exterior, so the operation of the refrigerator results only in energy being extracted from the water. So this is an important part. There is only energy being extracted from the water. Okay, so how much energy is extracted from the water in order to achieve this task? Well, we have QC that we are extracting is equal to mass of water, specific heat of water times delta T, and then the water becomes ice, so I have latent heat of fusion times the mass of water, because the whole thing turns into ice. So this will be equal to, so I'm trying to calculate the total energy extracted. This will be equal to 0.5 kilograms times 4186 times delta T. So this is going to be 0 minus 20 plus latent heat of fusion 3 times 10 to 5 joules per kilogram times 0.5. So that's the energy extracted from the water to turn it into ice, and then this has to be in absolute value so that it will be the energy extracted from the water to cool it down. So this is going to be my QC, and therefore my delta T will be found from coefficient of performance. QC is equal to 5 times the work done, so it will be equal to 2500 delta T. So I'm going to find that delta T is equal to QC divided by 2500, which is 83.3 seconds. All right. So this will be the total time it takes to freeze the water. Now, practically it will take longer due to leakage of energy and energy removed from the container as well. So this is not realistic. Why is it not realistic? Because there is leakage of energy from the exterior. There is energy removed from the container and other parts of the refrigerator, etc. So we have good reasons to believe that this number is not very reliable.